Hey everyone, welcome. Today, we're going to crack the code on a super powerful math tool. It's a way to take functions that seem incredibly complex, maybe even a little wild, and turn them into simple, predictable patterns. Get ready because we're diving into the Maclaurin series, and you're about to see how it helps us make sense of, well, everything. So let's kick things off with a puzzle. Think about trying to predict the exact path of a satellite whipping through space, or the chaotic, swirling air flowing over an airplane's wing, even the wild up and down swings of the stock market. These things are all described by really, really complex functions. So the question is, how in the world do you even begin to work with something that messy? You see, on one hand, you've got these chaotic, kind of unpredictable functions. But on the other hand, we have these nice, simple, totally predictable building blocks called polynomials. You definitely remember these from school, just those easy sums of powers of x. So here's the big question. Can we actually use these simple blocks to build a bridge to help us understand all that chaos? Well, it turns out the solution is this really elegant mathematical recipe. It's like a blueprint for approximation, and it's known as the Maclaurin series. All right, let's jump right in and see exactly how this thing works. Okay, so here's the absolute key. The Maclaurin series is a tool that lets us translate a complicated function into an infinite list of simpler polynomial parts. Now, you might have heard of a Taylor series. This is actually a special kind of that. What makes the Maclaurin series so unique and so useful is that it's always centered around one specific, super convenient point, x equals 0. Now, what's really cool is how this blueprint is actually put together. And this isn't some kind of math magic, right? It's a really precise step-by-step process that lets us build that bridge from the complex stuff over to the simple stuff. Okay, I know what you're thinking. This formula looks a little intimidating at first glance, but let's break it down. Just think of it like a set of instructions for building our polynomial piece by piece. The first piece, f of 0, that just tells us where the function starts, right at x equals 0. The next bit, with f prime of 0, that matches the slope at that point. And the third piece, with the f double prime, that matches the curvature, how fast the slope itself is bending. You see, every single term we add to this series is like adding a new layer of detail. We start with the function's value right at our anchor point, x equals 0. Then we match the slope. After that, we match the curvature, or the bend of the function. And with each new term we tack on, our approximation gets better and better, hugging the original function more and more closely, especially near that starting point. So this really just highlights the key ingredients, doesn't it? It all boils down to understanding how the function is behaving at that one single point, x equals 0. And when you apply this recipe to common but kind of tricky functions like e to the x or sine x or cosine x, you get these beautiful infinite polynomials that are just surprisingly simple. And get this, these are the exact recipes your calculator is using to spit out those values in a split second. All right, so we've seen how to build a Maclaurin series, but the big question is, why? Why do we go through all this trouble of swapping a perfectly good function for this infinite series of polynomials? Well, the answer is all about moving from complexity to clarity. And this, right here, is the ultimate payoff. We take a function that's difficult, maybe even impossible to work with directly, and we replace it with a polynomial approximation that we can totally control and analyze. We're basically treating a big, complicated mystery for a puzzle we already know how to solve. So what's so great about polynomials anyway? Well, they're just ridiculously easy to work with. I mean, you can add them, subtract them, multiply them, no problem. Differentiating, integrating, it's a piece of cake. And for computers, which are basically just lightning-fast number crunchers, well, calculating a polynomial is trivial. This is a massive advantage in fields like physics, engineering, and even computer graphics. So this all leaves us with a really powerful final thought. The Maclaurin series is like a universal toolkit. It shows us that there's a simple, orderly recipe hidden inside even the most complex-looking functions. It's this incredible idea that fundamentally changes how we can see and, more importantly, how we can calculate the mathematical world all around us. Thanks for joining me.